Hi, this is Peter with CalcBook, and today we're going to be looking at a steel handrail design. So if we do a quick overview here, we are going to be utilizing ASCE 716 and the 2021 IBC. We're going to get our loading from ASCE 716 at section 4.5, right, which says we need to apply a 200-pound point load at any location, or a 50-pound per foot linear load, depending on which one is more. So typically we just space our posts at 4 feet so that those values are the same, and we can just use either one to do our design. For some other requirements, right, our height is between 34 and 38 inches, so we'll just use a maximum of 38 inches to determine our forces on the post. We'll use AISC 360 for our flexure design, shear design, and for our welded connections. And so for this design, the components that we need to check, right, we need to check the horizontal rail as a beam. We're going to check the vertical post as a cantilever beam, and then we're going to check our post weld to the stringer at the base for that moment. So let's take a look at our problem statement. Right, we're going to be designing the handrail system shown. So we have a 38-inch tall handrail, 48-inch spaced post. We're going to be using a pipe 1.5 standard and using ASCE 716 and the 2022 CBC or the 2021 IBC, same information. And we'll be checking the horizontal rail as a beam, a simply supported beam between posts, our vertical post as a cantilever, and then our weld, we're using a circular weld down to the stringer. So let's go ahead and open up CalcBook and we'll get started on the design. All right, we've got CalcBook open now, so go ahead and click into our AISC 15th edition, and we'll do the top rail first. So we'll do our member design, click into our flexure design and shear design modules there, and then we can go ahead and start selecting our shape type. So we have a pipe, and it's going to be a pipe 1.5 standard. And then we're going to go ahead and jump directly into our beam loading. Our beam length, right, is just the distance between the posts, so that's going to be 4 feet long. Our shear analysis will be at the 0 point or could be at the end. Our moment is going to be mid-span, and then our deflection also mid-span. And so we can get rid of our dead load or we can keep it. Technically, the code requires the load to be applied in any direction, so it could be downwards, which in case you would include this dead load, so we'll just keep it there. But typically it's going to be an outwards or inwards force as people push and pull on the railing. So let's go ahead and enter in our live load, right? The handrail is a live load, so we want to go ahead and make sure we do that. And in the problem statement, we showed a distributed load at 50 pounds per foot, but actually, it's a 200-pound point load or the 50 pounds per foot. And in this case, a point load at the midspan is going to result in a larger moment. So we'll go ahead and use the 200 pounds point load, midspan, and we'll go ahead and use our 1.2D plus 1.6 live, and that's going to give us a total moment of 0.33 kip feet at the midspan. So we go ahead and click on our flexure design, right? We go ahead and click into that, and we are good here with a 0.3 DCR, right? We will check our slender elements like we do for our member designs. In this case, it's compact, so we just go to chapter F8. And it's just going to be based on the yielding equation Fy times Zx, and our flexural strength is going to be 1.11 kip feet, so plenty of capacity there. Jump over to our shear design, right? This should be fine. We need to enter in a property here for the distance from the maximum 0 point from the maximum shear to the zero force point. In this case, it's going to be just half the span, so this is just 2 feet. And we have plenty of capacity for shear, so we're good there on the top rail. So let's go ahead and jump back into our main menu here. We'll go to the 15th edition, and now we can do our post design. So we'll go back into member. We'll click on our flexural and shear design. We'll take a look at our pipe, and then we're going to go click on 1.5 standard. So we've got that all set up. Jump into our beam loading, right? So our beam in this case is going to be the post length, which is 3'2", so 3.167 feet. Our shear analysis will be at the base, so at 0. Our moment analysis will be at the base, so at 0, and then our deflection will be at the end, so 3.167. In this case, since it is vertical, we do not want to use the self-weight. Our boundary conditions are different, right? We have a fixed free condition, since we're fixed at the base, and free at the end or the top of the post. And then we are going to enter in our handrail as the live load, the handrail force, which again is going to be that 200 pounds, and in this case, it'll be at 3.167 feet at the end of the post. And then we can toggle over to our 1.6 live load combination, and that's going to get us our shear and moment here at the base. So now let's go ahead and take a look at our calculations. So for the moment, right, we're pretty close here with a DC ratio of 0.92. And again, the section is still compact like we checked last time, so it's just going to be based off of yielding that FYZX equation, and we have that 1.11 kip feet of capacity. And for our shear design, we should be fine here, right? So for this property, it's going to be 4 feet from the maximum to 0. And again, plenty of capacity here in shear. So a little bit close on the flexure design. We may want to upsize to a pipe 2 or something like that. But we can leave it now like that for now. So the one thing we want to do before we go to the next calculation for the base is we want to just take note of our demands here, right? So we can just take the ultimate load for the shear and moment. So we have, let's see here, of our live load, we have just 0.2, right? So 2 kips or 200 pounds of shear. And then we are also going to have for our moment, oh, I'm sorry, let's take the ultimate load here. So we have 0.32, excuse me, of shear. And then here we have 1.01 kip feet of moment. And that will come in handy as we go to our weld design. So let's go back to our main menu. We will go to the 15th edition again, connection design. We'll go to our welded tabs here, our welded design modules, and click into the round weld design. So for us, the outside diameter of a 1.5 standard pipe is 1.9 inches. The weld leg size, we can leave it at 1/4 and see if we can come back and optimize that. And then for our demands, since we already have the ultimate loads, right, we don't need to use our load combinations. So we can just go directly enter in all of the different ultimate combinations from, or the ultimate loads from our post design. So for us, in the X direction, right, we can just enter in our shear force, which is going to be 0.32 kips. No load in the Y direction. No load in the Z direction. We could maybe add some self-weight, but we don't need to do that here. And then our moment is going to be about the Y-axis, right? Because our force is in the X direction, so our moment's going to be about the Y-axis. And that's going to be 1.01 kip feet. All right, so we're showing a DC ratio of 0.77 with a 1/4 inch weld. So let's go ahead and take a look at our loads here. So our demand on the custom round weld, right? We want to first develop our section properties. So get our radius, our total length of weld, and then our section modulus and our torsional constants. And then we look at the weld stress due to each component. So in this case, we have loading in the X direction, so we just divide that by the total length of the weld. And then we have moment about the Y, so we take that about our section modulus. And then we just combine those two different directions using square root sum of the squares, and we get a total shear per linear unit length, in this case inches, of 4.2 kips per inch. And then for our capacity, right, it's just a standard fillet weld capacity check. And we have 5.57 kips per inch, so we have a DC ratio of 0.77. So that is a handrail design in CalcBook. We hope you enjoyed the video. If you have questions or suggestions for other videos, please let us know in the comments below, and we'll see you next time.